let's say, conflict between the two basic principles, one of general relativity, the other of quantum mechanics. What's the basic principle of general relativity? It's the principle of equivalence, which Einstein admitted. Well, he didn't give Galileo credit. I think he should have given a reference to Galileo. I'm not sure he did, because Galileo already noticed the principle of equivalence, and he talked about. I like the one of the fireworks. He says he describes his fireworks go out, and they make this beautiful sphere of sparks. As it falls, it remains a sphere. You can get rid of gravity by free fall, locally. I mean, he's very explicit. Not just the big rocks and the little rocks, and why the feather doesn't because of air resistance and all that. I mean, he was right. But, of course, you needed special relativity and make that into a four-dimensional space-time, as Minkowski did, and then bend it as Einstein did.
So the collapse and gravity come in?
Nothing there. But my argument is that the principle of equivalence, which is the basis of general relativity, is in conflict with the principle of superposition. And the argument is more or less this. I say, think of an experiment done in a lab on a tabletop, and you want to take the Earth's gravitational field into consideration. Now, there are two ways you might do this. The way any sensible physicist would do it, you put a term in the Hamiltonian. If you don't know what that means, don't worry. Put a term in the Hamiltonian for the gravitational field and just chug away, the usual procedures. Fine. Then you notice that Einstein's sitting in the corner, or Galileo even, and tell you, no, you shouldn't do it that way. The gravitational field of the Earth is locally just like free fall. Mm-hmm. So you can consider your lab, your coordinates are falling, and the lab is just accelerating in this thing. And there's no gravitational field. Okay, you do it this other way. It's a different way. Different coordinates, you do it away, and eventually you come up with almost the same answer. The key, of course, is in the almost. The wave function you get is just the same, except for the complex multiplier, the phase factor, right, if you like, which people would quite like to discard, because when they're going to measure anything that you observe, they're taking amplitudes, you take squares of moduli. So you don't worry too much about that. Until you look rather too carefully at this actual factor, which is different between these two procedures. That actual factor involves the time, an exponential of the time cubed. And that is not that serious if you really think of it. If you're thinking of quantum field theory, that's serious because that's telling you that's a different vacuum. You're actually working in a different vacuum. So you might say, well, you still might say, who cares? Because you say, stick to your vacuum, and you get the right answer at the end. Okay. So I'm going to change the problem a little bit, rather seriously, actually. I'm going to say that in this experiment, there is a lump of some sort.
Okay.
Which is put into a superposition of two locations. So it's a little stone, which goes into two places, or a little bead or something, which is part of the experiment. Now, I try to use the Galilean Einsteinian perspective, and I ran into trouble, because as I get close to the bead, I see whether it's here or here, I can't get rid of them both at once. And that's, of course, the Einstein problem, which led to general relativity. I can't get rid of them both at once by free fall. So what do? I do what any sensible physicist would do. I cheat. I say, okay, I know I should be using the Einstein perspective, but let's just try instead measure the mistake that I'm making by adopting that, by the Newtonian perspective. So I adopt the Newtonian perspective, but keep track of what might be a little error in doing it. Then I integrate that error over space, and I do a little integration by parts and some little bit of fiddling around with it, and I get with an answer which looks like a uncertainty in the mass of the system. It is the mass of the system, but it's not the the fact that it's a superposition it gives me an uncertainty of that mass. Now I can measure, and now the thing is, that's a bit like particle physics, where if you have a decaying particle, its mass is not completely well defined. It has an error, a fuzziness in its mass, which is given by the Heisenberg time-energy uncertainty principle. So its lifetime, if it's an unstable particle, is inversely related to this sort of fuzziness in its mass. Now here I have a fuzziness in the energy of the system, the mass energy of the system. So I say that's the reciprocal of that in natural units is when I say natural units, I mean making all the things equal to one that you can do, as Dirac sort of initially pointed out, I guess. And I get the formula, which Dioschi had already discovered a couple of years earlier than me.
Right, for different reasons.
I didn't know he'd done that. It was a different argument. But I thought this was a nice argument because it just revealed the tension between these two very basic principles, principle of equivalence and the principle of superposition. And they're a bit in conflict with each other. And the resolution of this conflict comes through allowing your unstable state to collapse into one or the other. Now, it's what you only get from this way of looking at it is an uncertainty in the mass. And I know that Yvette's looking directly at this thing rather than looking at the collapse, which is a powerful thing to exploit.
And just for people who are wondering about Yvette Fuentes, there's a podcast on screen right now where we go into 2 hours in depth into this topic. Now, do you have a mechanism for why or how gravity collapses the wave function? Or do you just say it has to, a collapse has to?
That's where the new theory has to come in. I'm just saying, look, I have a problem, I need a theory. No, all I can say is that it tells me how big the factor should be. You see, it tells you can measure this uncertainty, and it's not so hard. You just think of the bead that I was looking at. Imagine there are two copies of the same bead, and I move it into this superposition, and I ask how much energy would that cost me where I ignore all forces except gravity. Very tiny usually, but it's nevertheless, it's enough to collapse the state for even a flick of dust will collapse in a very short period of time. So it gives you that much. I mean, it's the same as Dioschi. It's the same formula. It's not a theory in the sense that his was. I mean, I think his ideas got, as far as I'm aware, rather shot down by the Grand Sasso experiments, was it? There's the thing, they took this thing down a mine shaft or something. No, it's to do with the heating. They anticipate bodies spontaneously heat, which I don't want. That shouldn't happen. But that's because the collapse has a very curious... You see, if you want to make it consistent with special relativity, don't worry about general relativity at the moment, you're really already in trouble. Because you imagine a body splitting, it's the superposition. It's not two bodies. It's one body, superposition of here and here. They get very far away from each other. They haven't collapsed yet. And now they're going to collapse. One goes. In whose frame does that happen?
Mm-hmm.
Is that a frame you should be talking about? How do you make that consistent? Well, what you've got to do, I'm not worried about that. Lots of people seem not to worry about that. I'm worried about that. You say, okay, the only thing you can do, which is relativistic, I mean, there are other wrong routes you can take, which I won't go into because it's quite a bit of a more story than I'm making out here. The only route you can take is to say the collapse actually took place right back to where the split initially took, and then there was only one route. But what about the other route? Well, what I have to do is to describe things in terms of two different kinds of reality. One of them is quantum reality, and one of them is classical reality.
So one doesn't give rise to the other? They're actually separate?
Well, it's the quantum reality, if you like, which does give rise to the way that the classical reality behaves, but it does it in a kind of retrocausal way. So that's what's so confusing.
In a kind of retrocausal way? Or is it retrocausal?
It's kind of retrocausal.
Okay, explain.
I'm saying this deliberately because it's only quantum reality. You see, this is a puzzle I think it was a puzzle I had. And you can resolve this in a rather peculiar way. You might say, oh, sure, if it was retrocausal and it went back to the beginning, then how do you, what am I trying to say? You can travel faster than light. Yeah, you can travel faster than light or backwards in time or something. Sure. So I've got to tackle that problem. Or you can signal backwards in time. That's the thing.
And you were trying to retain special relativity before.
Because I'm just saying you can't do that. Because, you see, think of Alice and Bob. I had this in some notes which I circulated, but I don't think it was actually published. It's sort of pseudo-published. You see, I have a book, the book I wrote, which was with the Princeton University Press, called Fashion, Faith, and Fantasy in the New Physics of the Universe. The fashion was about string theory, which I'm not sure was still so fashionable now, but it was then. Faith was quantum mechanics at all levels. And fantasy actually had to do with cosmology. It was to do with inflationary cosmology, because I simply thought inflation is much too fantastic. That's another story. But the fashion, so I had to write this new preface. They're going to bring it out. It's out now. I think it's almost out now. A new printing of Fashion, Faith. I wasn't allowed to change anything in the book, but I was allowed to write a new preface. And I do give an outline of this idea. I think I do. The retrocausal thing. You see, the thing is, think about the standard EPR. So you have a spin zero state, splits into two halves, spin half, and Alice takes one off in the spaceship and Bob takes it up on another half. Alice makes a measurement. What do I say happens to the quantum reality? It's a quantum measurement. Quantum reality propagates along the path light cone. What could be crazier than that? The backwards way, along the path light cone. It hits Bob's world line way earlier than he does his experiment. So his state is already changed into the one which is the opposite of Alice's state. Bob makes his measurement later. He doesn't know what the state is. Alice can only communicate classically with him. This is a quantum information. Now, quantum reality information. Quantum reality, you cannot measure, you can only ascertain.
Explain the difference between ascertaining and confirming. Because when you were on stage with Sabine Hassenfelder, you said, you can confirm at, I think it was the classical level, you can confirm.
And you can confirm.
Whereas at the quantum, you can ascertain. Like you can ask a question.
That's right. Well, you see, that it's really Einstein. It's Einstein's fault. Because he was saying, I think a lot of people were worrying about the reality of the wave function. Is it real? Is it really there? Not real, it's complex, you see. It's not real in the sense of real numbers, but is it really there? And Einstein produced the statement. He said, well, a concept of reality is introducing, which is if there's a measurement you can make on the system without disturbing it, and which with 100% certainty gives the answer yes, then that measurement is revealing an element of reality. So he says that the quantum state is real in that sense. What he didn't say, as far as I'm aware, is that is quantum reality. It's not classical reality. Think of the spin of a spin-half particle. I think I always like spin-half particles.
Sure.
It's the simplest thing to say. Spin up and spin down, if you like, or spin right and spin left. Suppose its spin is about that way. If I know through its origin, where did that spin come from? Oh, yes, I know. Oh, it should be spinning that way.
Wait, sorry, is this a hidden variable that it's carrying with it?
It's not hidden variables. Forget about Bohm.
Forget about Bohm.
I had
You're not a fan of
endless arguments with Basil Hiley on that topic, and I prefer not to go back there when I was at Birkbeck College.
All right.
Let's not talk about hidden variables. If you can call them hidden variables, you can, but that's not my idea. It's not that.
Got it.
It's quantum reality. So this state is that, but it has a quantum reality of spinning right-handed about that particular direction. And we know it is because we've set up and we've produced it in that state. You could do that by some experiment, and it comes out in that state. Now, I'm going to use Einstein's criterion. I can measure the spin in that direction using, as long as it's got a magnetic dipole or something, I can measure it, and I can if I've got it right, every time I measure it, I will get, or I can measure the same experiment many times over. 100% certainty, that's real. That's what Einstein said is his element of reality. I'm just slightly modifying what he said. It's an element of quantum reality. It's not classical reality.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.